just going to show you today some alternative ways of looking at integration by parts. This first method, I've listed it down as tic-tac-toe. So we know that it's the integral of u to v. So in my little table here, I write down u to v. U goes in the diff column, to v goes in the int column for integrate. Now, if I integrate to v, I get v. So that's the tic-tac-toe part. You go tic-tac-toe. Now, you differentiate the u, but you keep integrating as you go down. So under v would be the integral of v, which is whatever the integral of v is. So then I go tic-tac-toe. Over here on the right-hand column, it changes from plus, minus, however far down you have to go. And so I now go minus these two multiplied together, which gives me v to u. All right, it's easier to see it with an actual question rather than a formula. So u still is the same rules. U has to be chosen so the differentiation is a simpler function, and to v, obviously something that can be integrated. So exactly the same rules there. So first case, this is probably the best case we use it for, when you have a polynomial times some integratable function. So in this case, x times cos x. And you keep differentiating until you get the polynomial down to 0. All right, so x is going to be my diff, cos x is going to be my integration. I'll differentiate down until I get the polynomial to 0. So I need to do that twice. And then I'll integrate and so on. And now I just go tic-tac-toe. Tic-tac-toe, so it's x sine x. Tic-tac-toe, minus cos x. There's our answer. So it's just a different way of setting out the working. Let's try another one. X squared times e to the power of x. So this time the polynomial is x squared. So I differentiate until I get that to 0. X squared goes to 2x, goes to 2, goes to 0. And, well, integration of e to the x is a bit boring, but it goes e to the x, e to the x, e to the x. Notice plus, minus. And here we go. Tic-tac-toe, x squared e to the x. Tic-tac-toe, minus 2x e to the x. Tic-tac-toe, plus 2e to the x. There's our answer. So it works really nice with this sort of one when you've got a polynomial times something. All right, what happens if we get a polynomial times something you can't integrate? So in this case, I'm going to stop when the product of the line is integratable. So let's just do log x. Because we don't know how to integrate log x. So it'll be log x times 1. So I'm going to stop when the product of the line is integratable. Well, 1 times log x, I can't integrate. So I go to the next line, 1 on x, and if I integrate 1, I get x. 1 on x times x is 1. That's integratable. So tic-tac-toe, x log x, but, oh, hang on, minus the product of the line. So you notice in this case, I don't keep going with the integration. I just say, well, I stopped at that product of the line, and I'm saying, okay, I've got to integrate that one. So I've still got some integration to do for this one. Integral of 1 is x, and so we get x log x minus x. Try another one, inverse tan. So inverse tan times 1, no, can't integrate that, so I'll keep going. Differentiate, I get 1 on 1 plus x squared times x. So if I had x on 1 plus x squared, yeah, I could integrate that one. So I'll stop there. Tic-tac-toe, x inverse tan x, minus, and then the product of that line I stopped at. X, that when you think about it is simply integration by parts anyway. Because all I'm really doing there is uv minus v to u. So it really is the same thing on that. And we go and integrate it. There's our answer. X cubed log x. I can't integrate log x. Well, actually I can, because I could say it's x log x minus x, but let's pretend we can't. Okay, so I can't integrate log x, so it becomes the differential. So I'm going to keep going until I get something I can integrate. Differentiate log x, I get 1 on x. Integrate x cubed, I get a quarter x4. Multiply those together, I've got something I can now integrate, so I'll stop there. Tic-tac-toe. Then it's minus the integral of a quarter x cubed, and then we just integrate that. Now, as I said, actually, we do know how to integrate log x. X log x minus x. Let's do it that way. Now this now becomes a polynomial times something we know how to integrate. So I will just keep differentiating the polynomial. There's 3x squared. Oh, but hang on a sec. I've now got a problem here, because how do I integrate x log x? So I'll stop like I did before, and it becomes, 3 times integral. Oh, but no, when you look at it, hang on a sec. I've got 3 lots of x cubed log x, which I can move to the other side. So I get 4 lots of the integral of x cubed log x is that expression there. Integrate the x cubed, divide by 4, and we get the answer. Well, there's no prizes for guessing which way round is a better way of doing that question. So let's not try and be fancy, because yes, I knew what the integral of log x is, but it really did not save me any time. Let's do the logical thing for that one, which would be the first way of doing it. All right, case 3. I've got 2 integratable functions. So again, we will stop when the product of the line is integratable, or it's a multiple of one of the other lines. E to the x cos x. It doesn't matter which one I choose, because they're both integratable and they're both differentiable. So differentiate e to the x, we get e to the x sine x. Now stop when the product of the line is integratable. Not integratable. And it's not a multiple of another line, so I'll keep going. Tic-tac-toe gets me the first bit. Now let's do the next line. E to the x minus cos x. That is now is a multiple of the first line. So that's where I'll stop. So we go tic-tac-toe for the bit we've got, but then it will be plus the product of that line. So plus e to the x times minus cos x gets us minus e to the x cos x. That I can move to the left-hand side, and I get 2 e to the x cos x is equal to, and so on, divide. And we have it. Now, most of the time with this method, you just see it, case 1 is what it's used for. But what I guess I'm showing you is it can actually be used for other ones as well. I mean, whether it's a great method for the other ones or not, well, it's for you to decide. So some other examples. X e to the x, and somehow my dx has ended up in the power. No, it shouldn't be in the power. Okay. X e to the x. X is a polynomial. So I'll keep differentiating until I get to 0. Integrate e to the x, get e to the x, e to the x. Tic-tac-toe, tic-tac-toe, and we have our answer. So brilliant when it's a polynomial times something. It works fantastic. Inverse sine of x. Okay, differentiate inverse sine. I get 1 on the square root of 1 minus x squared, and that's times x. That line is integratable. So that's where I'll stop. So we get x inverse sine x, but then it will be minus the product of that line. So x on the square root of 1 minus x squared, which we can do, ends up being the square root of 1 minus x squared. Okay, square root of 1 minus x squared on x squared, and integrate the 1 on x squared. I think that's the easier way of going. So differentiate the minus x on the square root of 1 minus x squared, and that'll be times the minus 1 on x. That product now is integratable, because I'll end up with 1 on the square root of 1 minus x squared, which is the inverse sine. So tic-tac-toe, minus that integral, so minus becomes minus dx on the square root of 1 minus x squared, which is inverse sine. Here's another way you could do it. And okay, this is for a very specific sort of way of doing it, but remember, e to the iota theta is cos theta plus I sine theta. So back to this integral, e to the x cos x dx. Well, that's the real part of e to the x cos x plus I sine x. So all I've really done is added in that e to the x I sine x, but it's imaginary. So it's like I haven't added it there at all, because I'm saying it's the real part of this. So I don't really care about that imaginary part. Why do that? Well, because now inside the parentheses I have cos x plus I sine x, which I can change to e to the ix. And remember, it's the real part of all this. And then I can use my index laws and go, what I want to integrate is 1 plus I x. Or e to the power of 1 plus ix. Now 1 plus I is still a number, so we integrate it as normal, where we divide by 1 plus I in this case. And so our answer for this integral will be the real part of 1 on 1 plus I times e to the 1 plus ix. Well, realise the denominator, and I get 1 minus I e to the power of 1 plus ix, which is the real part. Okay, what have I done here? This e to the power of 1 plus ix. Index laws, what I'm really seeing there is e to the power of x times e to the power of ix. So the e to the power of x I have factorised out, because that's real. But the e to the ix I've changed back to cos x plus I sine. And so I want the real part of that product. So it would be 1 times cos x, and then the minus I times I sine x, which would be plus sine x. And we get our answer. Anyway, it's another way you could do that sort of integral.